Hi all, this is Mr. Yeager looking at, again, energy for a little bit. I have done another video, probably more geared toward the AP Physics 1 level about total mechanical energy and the work energy theorem. This one, it can be helpful at that level, but I think it's more geared toward the on-level physics. In on-level physics and in AP, we've gotten to the point so far where we have gone over work. We've said that work is a change in energy, that it equals F times D or FD cosine theta if you happen to be pulling the object at an angle. So that's kind of the beginning here is we've already gone through this idea of what work is. We have introduced the formulas for kinetic energy and gravitational potential energy. Again, we focus more on work being FD or FD cosine theta. What I'm trying to really go in more detail about this time or make more understandable is that work is a change in energy. So we've been saying work is a transfer of energy. It helps put energy into an object or take energy out of an object. The thing is, I want to describe what type of energy, because you can see this is just delta E. That's triangle delta E. So that means it can be any type of energy, because as we've been saying, energy is energy regardless of type. So work can cause a change in kinetic energy. If I start pushing an object, it'll start moving faster. Work can cause a change in gravitational potential energy. If I lift an object, I increase its gravitational potential energy. So work causes a change in any type of energy, and as a result, if I'm given work, I could possibly calculate the velocity that the object will go if I tell you how much work I put into the object and you know the mass. I could also tell you how high I lift it if I, again, give you the mass and the amount of work that I apply. All right? So that's basically what we're getting into in this particular lecture is now kind of connecting work with a specific type of energy. Force times distance will still be important. It'll still be part of the equation you'll see. But, again, it'll make it clear where that, we'll see this transfer between types of energy, between kinetic and gravitational potential. Okay? So, before we get to that, we have what's called total mechanical energy. TME is the way I abbreviate it on most of my worksheets. You'll see it in some of the work that you do. Total mechanical energy. What that means is it's just a word saying it's the total energy of the object, regardless of what type it has. So, since we focus only on kinetic and gravitational, total mechanical energy equals the sum of the kinetic and gravitational energy in the object. All right. So this would be an example of airplanes flying through the air. It's actually basically the example we're about to do. That airplane is moving, so it has kinetic energy. It's above the ground, so it has gravitational potential energy. So what is the total mechanical energy of the airplane? We add up all of the types of energy, and that would be my total answer. Okay? And this is what work will change. Work causes a change in mechanical energy, which then can depend on what type you're changing inside of that. Kinetic and gravitational are interchangeable. Okay? One changes into another depending on the situation. Again, we're going to look at specific situations trying to say what's happening to the kinetic energy, what's happening to the gravitational potential energy, etc. Okay? So, the thing is here, all these bullet points are about the total mechanical energy. The total mechanical energy will stay the same if energy is conserved. The thing that is most confusing to those people, though, is I could have one total amount of energy, but the kinetic and gravitational can constantly be switching. What I'm saying there is, as one goes up, the other one must decrease, but they have to add up to the same amount, okay, if energy overall is conserved. So, if energy is conserved, the total mechanical energy stays the same, but it doesn't mean the kinetic energy stays the same. It doesn't mean the gravitational stays the same, but the sum of those two together stays the same. Total mechanical energy will generally decrease with friction. I mean, basically in almost all situations, really only one exception we're not going to get into. Okay. So it'll decrease with friction. So that would be where we actually lose mechanical energy, meaning one of these is lost, kinetic or gravitational, during the process. And you can either increase or decrease the total mechanical energy with an applied force. Again, the simple example would be if you think of me just pushing a chair to the back of the room, it starts at rest, I start pushing it, I'm giving the chair some energy. I'm increasing the energy of the chair. Vice versa, you know, if I'm moving the chair to the back of the room and somebody comes from the other side and pushes the chair in the opposite direction, then obviously it'll slow down. So sort of with this last one, it's like, is the object speeding up or slowing down? So what if we get a question where it just says you have this 5 kilogram object going 5 meters per second and it's 10 meters in the air, what is the total mechanical energy? Well, all I would do is I'm going, okay, total mechanical energy equals kinetic energy plus gravitational potential energy. So kinetic energy is 1/2 mv squared. Gravitational energy is mgh. And I would then just calculate. So 1/2 times 5 times 5 squared plus 5 times 10, I'm going to use 10, times 10. mgh, 10 times 10. And then I basically solve. So this would be what? 25, 125, 62.5 joules of kinetic energy plus 500, 5,000 joules of gravitational potential energy. So then the total mechanical energy is those two added together. So 5,062.5 joules of total mechanical energy. So that would be an example of a problem where they give you everything and they say, what's the total mechanical energy? The thing is, guys, be prepared where I could just say, what happens if the 5 kilogram object is going 5 meters per second on the ground and is on the ground? Okay, what is the total mechanical energy? Well, I still have kinetic energy because the object's moving, but there would be no gravitational energy. So in this problem, the second problem we just made up, the total mechanical energy is the kinetic energy of the object, and therefore my answer would just be 62.5. Okay, so understand, don't be confused. There's sometimes people get mad because they're like, it's asking about total mechanical, but it doesn't give me anything about the gravitational. That's just because it's 0. And that's your answer. I mean, it's not the answer to the total mechanical, but there is no gravitational. This is just an addition when both are present. If only one is present, that's your answer. The total mechanical is all kinetic, is all gravitational. But when both of them are present, we have to add them up. Okay? So that's kind of one general type of problem that you could see. The other ones that I like to use too is more conceptual, just saying, do you understand what all the types of energies are doing? Can you tell me if they are increasing, decreasing, or staying the same? So you can see in this situation, we have an apple falls from a tree, and it says ignore air resistance. So what does this mean? I have an apple up in a tree, it's above the ground. What's going to happen? It's going to fall toward the ground. So what does that mean about the gravitational potential energy? It decreases because as I get closer to the ground, it goes towards 0. So that would just be decrease. I'm not looking for numbers. I'm just looking for you to understand, is it going up? Is it going down? Is it staying the same? So the gravitational potential energy goes down as it loses height. But as it falls, it should speed up, which means it'll have kinetic energy. It'll increase in kinetic energy. So gravitational decreases as kinetic increases. What does that mean about the total mechanical energy? Well, if there is no air resistance, if there's no friction, that means this will stay the same. The total mechanical energy will stay exactly the same. What's happening, for example, would be, let's say this object starts with 10 joules of gravitational potential energy, with where it is. I'm just making that up. Since it's at rest, the kinetic energy right here is 0. So what's the total mechanical energy? TME would be 10 joules. Add the two together. When it reaches the bottom, right before it hits, the gravitational potential energy is now 0, but the kinetic energy is now 10. Because there's no energy loss. The gravitational must have changed into kinetic energy. So what's the total mechanical energy at the bottom? 10 joules. Did the energy change from top to bottom? No. Even if I look right in the middle, I could say right in the middle, I'd have GPE equal 5 and KE equal 5. What does that add up to? How about that? It equals 10. Okay? So it doesn't matter where it is, the mechanical energy the entire time is 10 all the way down. The gravitational energy is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Kinetic is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they are the gravitational and kinetic are perfectly changing from one type to another equally. Okay, as one decreases by one, the other increases by one, etc. Let's look at some other ones. A car accelerates over a frictionless surface. Okay, a frictionless surface. All right, I'll make it even clearer for you. A frictionless flat surface. Okay, so a car is accelerating. Let's maybe do the one that's clearest. It's getting faster. So what does that mean about the kinetic energy? It is increasing. Okay, I'm going to make this even clearer. Let's say a car speeds up over a frictionless surface, since we could technically say it's slowing down. So it speeds up over a frictionless surface. It wouldn't slow down on a frictionless surface, though. So KE increases. It's a frictionless flat surface. So what's gravitational energy doing the entire time? Nothing. It stays the same. It's 0. I don't want people to write 0 there. I want them just to tell me that it's equal. It starts at 0, it ends at 0, so it stays the same. So now let's think about this. The gravitational energy is staying the same, but the kinetic energy is increasing. When I add these two together, I get total mechanical energy. So if one of these two increases, then the mechanical energy has to increase as well. Okay? I mean, it only makes sense. 0 plus 2 is 2. 0 plus 5 is 5. It has to be increasing if one of the two energies is increasing while the other one stays the same. Okay? So that's it. Those are usually like the easy, quote unquote, easier examples because, I mean, if one goes up, the other has to go up. Like if kinetic energy increases, mechanical energy increases. If gravitational decreases, the mechanical energy has to decrease, etc. So they have to obviously travel together if you have one variable that stays the same. Now, what about this last one? The kid goes down a slide that has friction. So this is sort of like the apple. The kid's at the top of the slide and then reaches the bottom of the slide. So he has gravitational energy, and that is going to decrease as he goes down. So gravitational energy decreases. As he goes down the slide, he will increase in kinetic energy. He has to be going faster. It's not like he zooms and then slows down. He will get faster all the way down the slide. Okay, all the way down. So this is one where people get confused because they're like, oh, one goes down, one goes up, so total mechanical should stay the same, just like the apple problem. But this time there's friction. And friction always, always, always will decrease some of that mechanical energy. In other words, this gravitational energy is changing into kinetic, but it's also changing into heat because of friction, which we're going to call thermal energy. Okay? It changes into thermal energy, so all that energy is not making the object move, not making the kid move. It's changing some of that energy, obviously as the kid rubs against the slide, into heat. So the total mechanical energy does decrease. So I could start with 10 joules of GP up here, but only end with maybe 7 joules of kinetic energy down here. Where'd the other 3 joules go? The 3 joules left as thermal energy. Okay? So you got to be careful with that. When they are working opposite of each other, just look. Do you have friction or not? Is there air resistance? If there's not, TME is equal. If there is, it's most likely decreasing. I mean, it most likely is. Okay? Good. Right. So that's like one way that you'll see some problems with total mechanical energy. It's just calculating it and then kind of conceptually understanding how the energy is changing during a particular situation. But how do we get to the big calculations? This leads me to the ultimate formula for energy called the work-energy theorem, where basically I'm putting all these pieces together. Like I said, I wanted to bring work back into this. Okay? Work, what the formula is it's called work external. WEXT is work external will equal a change in kinetic energy plus a change in gravitational potential energy. Now, just because it says both doesn't mean both change. We're just saying work can cause a change in both, a change in one, or a change in the other. All right? It just depends on the situation. Okay? This work external is equal to force times distance, like we're used to. That is work. What we're going to be looking for in most of the problems, though, is when is there an external work? When is there something outside acting on my object? And what the force you're looking for, the forces you're looking for, is there friction or is there an applied force in the problem? If you don't see either one of those, there is no work external. Okay? I did not include gravitational force. Weight or gravitational force do not cause external work. Okay? They're going to be something that's called, they work internally. They will change the energy of the kinetic into gravitational, gravitational kinetic, but they do no external work. Okay? So only friction or any applied force will do external work. If not, we will ignore that. The other thing that we will call this sometime is we'll sometimes call the work external the thermal energy. Okay? The thermal energy. And I'll come back to that a little bit later, but just wanted to mention that now. Okay? So, the thing is, we have this formula, but how are we going to use it? I don't like keeping this the work energy theorem in this form. I know that's what it is. That's what you'll see in any textbook online or anything. But I like to expand it because I'm going to try to show you how to approach these mechanical energy, work energy problems. So what I like to do is I'm going to change the kinetic energy into final minus initial, and same thing with gravitational. So I get this formula, work external equals final kinetic energy minus initial kinetic energy. That's what this is. That's what the change in energy is, plus gravitational final potential energy minus initial gravitational potential energy. Okay? So, some people get scared by it. They're like, ooh, you just made the formula larger. Well, actually, I'm still not going to leave it like this. I don't like these minus signs. So what I'm going to do is I'm going to add the initial energies of both types to the other side. So that leaves me with a formula of, let me start this again. Kinetic energy initial plus gravitational potential energy initial plus work external equals kinetic energy final plus gravitational potential energy final. That is the formula that actually I prefer and that I encourage. On one of my worksheets, basically that's written on every single problem for you to see. I like this particular formula because it can help you think how to look at this problem. Whenever you get an energy problem, you want to know what type of energy does it have initially. Does it have kinetic energy? Does it have gravitational energy? That's all on one side. So what type of energy does it have at the beginning? Then, is anything doing work on it? Is there friction? Is there an applied force? Those are basically the questions I would be asking. And then, afterwards, what does the energy look like? So basically, this is a good snapshot. It's telling you this is the initial mechanical energy. This is the final mechanical energy. All right? Is there any work being applied in between? If no work is being applied, then the sum initially has to equal the sum finally. But the energy types can change. And again, that's where people get confused. They're like, what? The energy's changing, so the overall energy's changing. No. I could have 2 plus 8 equals 10, and this 5 plus 5. That also equals 10. Doesn't that tell me that the mechanical energy stays the same? Yes. What happened? Some of the potential changed into kinetic. That's all we're trying to illustrate here in these situations. So, if I write that out, when you're given a situation, this is how I approach every problem with that formula. 1, what type of energy do you have initially? What types of energy? I'll put a parenthesis here because you can just have one. What types of energy do you have to begin with? Okay. 2, is any work being done? All right. In other words, like I've said a bunch of times, is there friction or is there an applied force? If the answer to that's no, work external is gone from this equation. The thing that I love about this initial equation, never mind, is that while it looks huge, there'll be plenty of things that are zero. You'll go through the problem and go, is the object moving initially? If the answer is no, you have no kinetic energy. And so maybe all you start with is the gravitational potential energy. I like the formula because I like to see students cross things out and go, hey, I don't have this, so I don't need it. And it reduces the formula to something much more simple. It is actually fairly rare that you need all 5 of these variables. Okay? So just be aware of that. So is any work being done? And then finally, okay, what type of energy, type or types, do you have at the end? Okay? Is it moving? That means you have kinetic energy. Is it off the ground? That means you have gravitational potential energy. So it just depends on the situation. So let's try a couple problems here. Okay? And you can see I have my formula up there already. So what I have here is I have some sort of roller coaster at the top of a hill. It starts at rest. The v equals to 0. It's 40 meters up this hill. My question is, what is the velocity at the bottom of the hill? And let's say the hill is frictionless. Okay? So how do I approach this? Let's go through my 3 steps. 1, what type or types of energy do I have at the top? Do I have kinetic energy? No. So that KEI is gone. Do I have gravitational potential energy? Yes, I do. This object will have gravitational potential energy. It is off the ground, 40 meters. So I have gravitational potential energy initial. Is there any work being done? Is there any friction? No. Does it talk about any applied force? No. So guess what? This is gone. So the only thing that I start with on the left side of my formula is initial gravitational potential energy. Let's go to the other side. Okay? At the end, the roller coaster is on the ground. So, will it be moving? I sure hope so. Once this thing starts going down the hill, it's going to speed up and speed up and speed up and speed up, obviously. So yes, of course it has kinetic energy. Does it have any gravitational energy? Well, it's on the ground. So the answer to that is no. So this problem from that 5 variable initial equation is just gravitational potential energy will equal the final kinetic energy. So that's not my answer. My question is, what is the velocity that I have? So now I go back and now I start using my energy formulas that you've been practicing for a week. mgh, now I like to write an I right here because later on we might have a different h. There might be multiple h's. So I write hi for initial height equals 1/2 mv squared. All right. Now one thing people get a little worried by is I never give you a mass. We never said what's the mass of this object. The thing is, we don't care because mass is on both sides, which means it cancels out. If mass is in every part of the equation, even if there's like a plus sign and something else over here, it has to be in every type before you can cancel out. So this one cancels out. So now I'm left with GHI equals 1/2 V squared. This would be, I'm going to again use 10. 10 times 40 equals 1/2 times V squared. This would be 800 equals V squared. Let me grab a calculator. 800 square root 28 meters per second. So this object would be going 28 meters per second at the bottom of the ramp. Now one thing I always like to mention, just kind of added on to this, because the mass gets canceled, every object, because it's frictionless too, every object will be going 28 meters per second at the bottom of the ramp. It's basically the same idea that gravity is going to pull all objects down the same. It's going to accelerate everything the same. So it doesn't matter if a mouse that's sliding down this or an elephant that slides down this, they both will be going 28 meters per second by the bottom of the slide, as long as there's no friction. Okay? All right, let's look at a different problem. Okay, there's a different problem here. All right, let's say I have this little roller coaster. Okay, 1, 2, 3, 4. Okay, so let's say I have this roller coaster at the top of the first hill, and again it starts at rest. And this hill is going to be 35 meters. 2 is on the ground, 3 is 28 meters, and 4 is 15 meters. Okay, my question is, what is the velocity at point 3? What would be the velocity of the cart at point 3? Okay, and again, I'm going to say that this surface is frictionless. We'll do an example where it's not frictionless in a moment so you can see what happens. Okay. So, since it's frictionless, you can immediately already eliminate work external. That's gone. Okay. We start this problem all over again. Look at where it is at the start. Is it moving? Once again, no. Is it above the ground? Yes. So we have gravitational initial energy again. This will equal. All right. Any time that this object is now below this height, below the 35 meters, it has to be moving. So we can talk about it. As it moves down, it'll get faster and faster and faster and faster, reach maximum speed right here because all the energy is now kinetic down here. But then what happens is it starts going back up. It's going to slow down. But will it stop completely? No. There'll be kinetic energy and gravitational potential energy right there. I am above the ground, so I have to keep that. And it's moving, so I have to keep the final kinetic energy as well. So both of these stay. Okay. So now I can solve. Now, some people do stop me and go, wait a minute, don't you need to solve for what's the velocity at 2? No. If the surface is frictionless and you get like this multi-path situation, you can start anywhere you want as long as you have information about that spot that you're starting at. You don't have to sit there and go, let me find 2, and then 2 finds 3, and 3 finds 4. No, you don't need to do that. I'm going to start at 1. If I wanted to figure out the velocity at 2, I'd go 1 to 2. If I wanted to find the velocity at 4, I'd go 1 to 4. And I'd ignore everything in between. It would basically be like I just slid past it and went straight there. Okay? So I'm only looking at 1 and 3. So if I set this up, mghi equals 1/2 mv squared. I'm going to write final because, again, sometimes there's initial velocity. We haven't done any yet. And then mghf. So that's why I write the subscripts I and f, because I have 2 different heights. The first height is 35. The second height is 28. So there is a change in height that occurs. All right. Once again, I can cancel out mass. There is no mass. Like, it's in every part of the equation. It's right here, and it's right there. So I can cancel it out everywhere. So that now leaves me with 10 times 35 equals 1/2 vf squared plus 10 times 28. Okay? So that leaves me with 140 equals vf squared. I got 140 because 350 minus 280. Just going a little bit faster. Okay? And then I take the square root of that. So this v will be, I think, 11. Well, yeah. 140 square root. 140 square root is 11.8 meters per second. That would be your final velocity. Okay? Now, I could ask you, rank the velocities of 2, 3, and 4, where we just already went over it. 2 should be the fastest, followed by 4, followed by 3. So even if you're calculating it, hopefully you go back and go, okay, this should now, like if I want to calculate 4, the velocity should be higher than 11.8. Okay, you should be able to see that. All right, last question. One more question. All right, this last question is stating that I have a child on a slide that's mass of 21.7 kilograms. They're on a 3.5 meter high slide. Okay? And when they reach the bottom, they have a velocity of 2.2 meters per second. So it's already giving you information for gravitational at the top and kinetic at the bottom. The question is saying how much thermal energy is lost. How much thermal energy is lost. So what they're saying is, if you do mgh, 21.7 times 10 times 3.5, that number will not equal 1/2 times 21.7 times 2.2 squared. They are not equal. So energy has been lost. The thermal energy comes in at the work external. And since energy is being lost due to friction, okay, the idea is there's friction on this slide. It's not frictionless this time. Energy is going to be taken from the initial. So while this is always written as a plus sign, if there's friction and energy decreases, I'm going to change this to a minus sign, and I'm going to write this as TE instead of work external, because I'm going to call that thermal energy. But then I go through the problem normally. The kid is not moving at the top, but he is up high, so GPEI minus any thermal energy lost will equal, I'm moving at the bottom, but I'm at the bottom, so 1/2 mv squared. Can I sorry, getting ahead of myself, Ke. So let's write out my formulas, mghi. There is no formula for thermal energy that we use, and that's what we're solving for, so we can just leave it as Te equals 1/2 mv squared. So here's the common error. So far, every single problem, we've canceled out the mass. The thing is, while the mass is in mgh and in 1/2 mv squared, it's not in Te, so I can't cancel it. You can only cancel it if it's in every single variable. Okay? So I need to use it now. 21.7 times 10 times 3.5 minus Te equals 1/2. Running out of space, 21.7 times 2.2 squared. If you go through the whole problem, you will find out that you will have a thermal energy of 691 joules, or something very close to that. All right. All you're doing is solving for Te. So calculate, basically subtract to the other side, and then obviously get rid of the negative sign. Okay. So 691 joules would be the final thermal energy. Okay. So you're going to be practicing other problems with it. This is your main formula at the top. I'll go to the next page. I think I have it there. This is your big formula. What energies do you have to begin with? What energies do you have to end with? Is there anything that's acting on it that might increase or decrease the energy of the object? Is it slowing down? Is it speeding up over time? Okay. So those are the types of questions to ask, and then from there you're good to go.